name is Martin, and I quickly want to present our work on dynamic and efficient gray box hyperparameter optimization for deep learning. Our motivation is as follows. So far, mostly they are black box and gray box methods, where black box method we sample a configuration and train it until completion, whereas in gray box we actually consider intermediate performances and use that to possibly early stop configuration. One example is, for example, Hyperband, where we have a predefined policy on when to consider stopping configurations and also a way on how many configurations to sample. However, that policy might be suboptimal, as we see in this example, where we see different learning curves. The accuracy, so the higher the better, and the color indicates at what time the learning curve has been trained. So the darker, the later in the optimization process. And what we clearly see is that the policy is suboptimal, since there are training curves trained until completion, like this one, even though we have seen better performing ones earlier in the optimization process. So what we would like to see is something as we see here, that the darker the learning curves get, the better they get. And that was our main motivation in DyHPO to actually achieve such a method. So let's start quickly with the problem definition and notation. So we are in the gray box DyHPO setting, meaning we have a response function f that gets as an input a configuration and a budget and will return a validation score. We abbreviate the notation by denoting with Fij the validation score of the response function for configuration xi at budget j, and refer to the noisy observation of Fij as Yij, and similarly we denote the learning curve with the capital letter, so a capital Yij is basically just tuple of the ordered intermediate performances. So in fact, the DyHPO algorithm isn't any different to the standard Bayesian optimization algorithm. The main difference is what surrogate model and which acquisition function we use. So as a surrogate model, we still use a Gaussian process with a change in the kernel. So what we use is the kernel we see in equation 1, where K is the RBF kernel, and the phi is a neural network as shown down here. So that neural network gets a couple of inputs, for example, the configuration as well as the budget scaled to 0 to 1, which basically fed into some sort of MLP. Plus there's the learning curve up to that specific point, which is fed into a 1D convolution followed by a max pooling layer. And furthermore, we adapted the acquisition function, like the expected improvement, to the multi-fidelity setting with a very small change. So instead of using our Ymax, which is the global best score we have seen, we now have Yimax, which is the best score seen at a budget J. So let's quickly go over the results. So we consider 3 different benchmarks. Here we see basically the performance with increasing number of epochs with respect to the mean regret, meaning the lower the better. And our method is the gray one. So we see in these 2 benchmarks, it's showing promising results. We further did some statistical significance test. Here we see CD diagrams for this LC-bench task set at 50% of the budget and 100% of the budget. And basically a method is statistically significant better than another one if it's not connected with the bar. So we see in these 3 cases it is better than its competitors. So concluding, we have demonstrated how DyHPO can improve the performance in a gray box setting. We introduced a specific surrogate model which takes the learning curve as an explicit input, and we've shown a small modification of expected improvement. On diverse benchmarks, we have shown that this method shows promising results. Thank you for listening.